and it's 6 o'clock Eastern time, and who knows, I'm not going to go around the world, but I'm happy Hokuto Konno is coming from around the world to present to us, and I will let him take it away.
Yeah, thank you. So let me start sharing screen. Again, I uploaded to the slide on my homepage, so let me paste the URL to chat. Hopefully, you can see. All right. So, okay, so thanks for coming again. So this week I'm gonna focus on recent joint work with Masaki about well, the Seiberg-Witten theory for families of four-manifold with boundary. Okay, and but before starting, so let me give you one supplement to the last talk. So this is due to Danny. So after finishing the last week talk, Danny pointed me out there's an earlier result than Donaldson one in 1990. So as I introduced last week, in Donaldson showed that the natural map between pi zeros of leaf of case 3 and home of case 3 is not surjection. But before that, there's a work by Friedman and Morgan, 1988. So it says if X be smooth-oriented for manifolds homeomorphic to CP to endpoint grow up for n greater than 9, then the same sort of conclusion holds. Again, this map is not a surjection. And the proof uses the action of the diffeomorphism on Donaldson invariant. And additionally, of course, since now this manifold has B plus 1, so half the concept work closely somehow. And sorry, and Friedman and Morgan showed more actually for some X above rank of co-kernel of this natural map is actually infinity. So quite huge co-kernel exists in such a case. Like so this is supplement, and now I'm going to go to today's topic. So this topic is based on the paper on arXiv with this title uploaded to last October. And so here is a quite brief summary of this talk. So the main theorem today is an extension of Barguria's constraints on smooth family of closed form manifold, which I explained last week, to smooth families of form manifold with boundary using Froshov type invariants. So mainly I will speak about delta. So this is, I'm not sure. At least I looked at this notation first time in Chuprian's triangulation conjectures paper. But maybe probably in many places, H is more used commonly, probably, but this delta is minus H. And similarly, unrest Chuprian's alpha beta gamma invariant for spin case similarly. And so application is somewhat similar to the last week's story for a lot of form manifold X with boundary, such a natural inclusion map from the relative diffeomorphism group into relative homeomorphism group. So the notation relative diffeomorphism group is just the same. This is just a subgroup consisting of diffeomorphisms fixing the boundary pointwise. And so the latter is the normal one, just from a normal absolute diffeomorphism group into homeomorphism. So the statement is for a lot of form manifold X, these guys are not weak homotopy equivalencies. And the proof uses Chuprian's Seiberg-Witten for a homotopy type in an essential way. Okay, so this is a super quick summary, but let me give you a little more detailed overview of the talk. And so first, after finishing overview, I will state the main theorem today and describe applications which I have just explained. And after that, I will give you a proof of main theorem, because last week I didn't say any sort of a proof at all. So I tried to describe a proof a bit more in detail. And after finishing that, I tried to describe some refinement of the main theorem for the spin case using alpha beta gamma invariants. Okay, so let me start with overview. So first, let me remind you last week's story, Barguria's constraint. So this is given by David Barguria, 2000 90. So let X be a closed-oriented smooth form manifold, and let S be a species structure on X. And so here, now we have a smooth family of a compact base space, but the fiber of the family is a spin-C form manifold, and suppose that. So as I said here, I wrote. So as I said, if you have a fiber bundle with 4-dimensional fiber, you have some associated vector bundle of rank B plus, and let me denote by H plus E. And suppose that WB plus of this guy doesn't vanish, then we have such conclusion. So this says the Dirac index of the spin-C for the spin-C structure S is non-positive. Okay, so this resulting inequality is the same with the unparameterized and non-negative, negative definite case. So once if you have a negative definite for manifold X, and if you have such an inequality for every spin-C structure, it gives you Donaldson's diagonalization via Elki's theorem. And the assumption of the negative definiteness here is replaced with such assumption, non-vanishing of a certain characteristic class of H plus bundle. So as I explained, the feeling, at least to me, the feeling is like this assumption is saying like B plus is killed by B plus, and it looks like negatively definite. So I hope maybe today, since I'm gonna explain the proof, so maybe you might also can agree at least partially with this feeling. Okay, and as a good consequence of Bagria's constraint, you may say that so quite a lot of form manifolds simply connected and closed, smooth, indefinite form manifolds with the absolute value of the signature is greater than 8. This map is not a weak homotopy equivalence. Okay, and more precisely, actually, David showed much more. So this natural map between pi n is not an isomorphism for some n round up to B plus minimum of B plus and B minus. So
may I ask?
Yeah, sure.
Do we know what? So I guess we don't know which n it is. Is that correct? And do we know whether? Do you expect this is really showing that something is not injective or not surjective?
Again, in general, I don't know a lot. Of course, the trivial case is just if we can say that pi 0 of this map is not isomorphism. Actually, the proof is if we can detect pi 0 in this method, it says just we are detecting non-smoothable family over circle. So actually, in that case, we can say that the map between pi 0 is not surjective. But I suppose that's the only case in general. So, or yeah, at least in this method, since the base space is just a torus, so I have no good idea to say. So the feeling is that, as I explained last week, the feeling is a little like non-surjectivity result. And in some lucky situations, say, for example, if we consider like family over T2, two-dimensional torus of K3 surface. So in some work with David, we showed that like pi 1 diff over K3 to pi 1 home over K3 is not as surjective. So in very lucky situation, if we can kill the obstruction in lower dimensional skeleton, then we sometimes can show that this map is not surjection in some specific degree. But in general, I don't know any good way. Yeah. Okay. Yeah, so this is a good result. And so what we are going to do is to extend David's result to form manifold with boundary. Okay, so here's a strategy to attack diff versus Homeo for manifold with boundary. But the idea is quite simple. So as I explained, Barguria's constraint is constraint on smooth families of closure form manifolds. And on the other hand, you know, Froshov's result. Froshoff gave constraint on smooth form manifold with boundary provided to that manifold's negative definite. So, and both of them can be sort of extensions of Donaldson's diagonalization. So just put them together somehow. And then we get a constraint on smooth families of form manifold with boundary. So then probably we can get this kind of result. So that's the idea. And the technique is something as follows. So David used a finite dimensional approximation of a family of Seiberg-Witten equations. So a little more precisely, he utilized a family version of the Bauer-Futter invariant. And we need something like with boundary version of the Bauer-Futter invariant. And to do that, of course, we have to use Shiprian's Seiberg-Witten Fourier homotopy type. Okay. So, okay, here, this is a kind of schematic picture until here, summary of our aim. So our starting point is Donaldson's diagonalization every time. And so if we try to extend this guy to for manifold with boundary, then you have Frosch's constraint. And once you want to consider family version of Donaldson diagonalization, then you have Barglia's constraint. So what we aim is here, so with boundary version of Barglia's constraint, or alternatively, this is a family version of Frosch's constraint. Okay. And so before proceeding, maybe I better remind you that what is Frosch's inequality. So today I just only for simplicity, I will assume that the boundary component is connected. So let X be a compact, smooth-oriented, and negative definite for manifold with boundary, and assume that the boundary is connected and it's a rational homogeneous sphere. And then for every spin-C structure S on X, we have such an inequality. Okay. So the left-hand side is again the Dirac index, but the right-hand side something new appear. So this is the Frosch invariant. Okay, so I will explain the sign convention next slide. So anyway, so if you take Y to be S3, then this recovers Donaldson diagonalization because the Frosch invariant of S3 is 0. So then you get Donaldson diagonalization again. And some conventional remark is so if Y is an integral homogeneous sphere, as you know, if this guy admits unique spin-C structure Y, so I will abbreviate S and just simply write delta of Y. Okay, and so there are conventions on the Frosch invariant, but so today I will use this convention. Delta of sigma 2, 3, 5 is 1, or more generally. So if we wanna write H, it should be just a minus delta, and this is same with the half of the Frosch sorry, here Fourier correction term D. Okay, so this is convention. Right. So let me state our main theorem and describe the applications. Okay. So this is the main theorem. So let X be a compact, oriented, smooth form manifold with boundary with B1 equals to 0. So this is again assumption for simplicity. So probably I think we can remove this assumption, but let me suppose. And assume that Y is a rational, connected rational homogeneous sphere. Then let S be a spin-C structure on X. And let me have a smooth family of a compact base space with fiber spin-C for manifold X and S. And let me, so this is an important assumption. So assume that the restriction of E to the boundary, so precisely like a fiber-wise restriction to the boundary, then it gives you some family of 3 manifold. And now assume that this family is a trivial bundle of spin-C 3 manifold. So including spin-C structure, I will suppose this bundle is trivial. And here, let me suppose precisely the same assumption with Barglia's theorem, and WB plus of associated H plus bundle is non-zero. Okay, then you have the same conclusion with Frosch's inequality. Okay, so this is the result. Okay, so here is the kind of obvious remark. So if you take B, the base space to be a point, and B plus equals to 0, then this theorem is nothing but Frosch's inequality. And if you take Y to be S3, then the above story just recovers Barglia's constraint. So in such a meaning, this theorem is an extension of these two constraints. Okay.
So I have another small question.
Yeah, please.
If E, the restriction of E to the boundary is a trivial bundle.
Mm-hmm.
How could it, or maybe I'm missing something, how could it fail to be a trivial bundle of spin-Seith manifolds?
Oh, sorry, how can I?
Well, I would have thought that somehow spin-Seith structures are sort of some rigid thing.
Mm-hmm, mm-hmm, mm-hmm.
So how could that vary in a family if you have, especially if you have a trivial bundle?
So here just this says that not just isomorphism parts. So this says a very strict, strong sense, like including how can I say? Just now I don't vary the spin-Seith structure on 3 manifold bundle at all. This is
I see. So you're thinking of the spin-Seith structure as actually sort of a bundle itself rather than an equivalence class.
Yeah, not the equivalent class actually.
I see. Is there some sort of canonical example where those are different notions?
Yeah, actually, yeah, it's a good point actually, but my answer is no currently, because actually I consider that problem with David profile, and we thought that in most practical situation, actually, how can I say, like if we consider a family of the isomorphism class of the spin-Seith structure, actually almost every time we can lift it up to honest family of the spin-Seith structure. So we have a good example describing the difference of these two notions. But of course, practically, to get application to the diffeomorphism group, it's a good news, since we have to lift everything up to honest spin-Seith structure family to do Seiberg-Witten theory, parameterized Seiberg-Witten theory. Yeah. So actually, I didn't describe that point last week. Just it's a hidden part, but yeah. So thanks for asking. I should emphasize that point here. So to get such a theorem using Seiberg-Witten theory for families, of course we have to work on family of spin-Seith for manifold, so honest spin-Seith structure we need. But finally, we want to get next slide is okay. So finally, we want to get something relating to the diffeomorphism, not the automorphism group of the honest spin-Seith structure. So we somehow have to once lift everything up to spin-Seith structure level from the diffeomorphism group bundle. But it's very, how can I say, not quite difficult to work actually. Just in practice, it's not so difficult. Yeah.
Oh, okay, thank you.
Yeah, thank you. Yeah, that's a point. All right. So is there another question about the statement of the main theorem here? All right. Great. So then, then let me go to application part before stating before explaining the proof of this theorem. First, let me describe applications. So the first application is a comparison result about the reactive automorphism groups. So as a notation, as I said, so if I denote by diff of x delta, this means just a group of diffeomorphism fixing boundary point-wise. And similarly, let me define a homeo x delta. And the theorem here is an application of the last one. So let X be an oriented, compact, simply connected seems indefinite form manifold with non-positive signature, and assume that the boundary here, I maybe have to emphasize, assume that the boundary is an integral homogeneous sphere, not a rational homogeneous sphere. And assume also that the signature either this or this. So signature of X is less than 8 and less than -8, and the Froschel invariant is non-positive, or X is spin and minus signature over 8 is greater than signature, delta of Y, Froschel invariant. So actually these conditions are not so quite hard condition to check in practice, and then you can conclude that this natural map is not a weak homomorphic equivalence. And again, as well as the various result, we may say a little more precisely. So the natural map between pi n is not an isomorphism for some n less than b plus. Okay. Okay, I will give you example, but before that, let me say proof of the theorem, assuming the main theorem. Okay. So basically, the idea to prove this theorem is quite similar to the last week's story. So this is an adaptation of the argument with Kato and Nakamura and David. So what we have to do is first to construct topological family over B plus dimension torus somehow. So I will explain how to construct a little more precisely later. So anyway, let's construct a topological bundle satisfying that WB plus over H plus does vanish. So this means the assumption of the main theorem is satisfied, but the conclusion is not satisfied for some spin-C structure S. So this is, the opposite inequality to the Freischutz one. So this means that the conclusion doesn't hold for some n S. Then the main theorem says that E is non-smoothable bundle. So here, in this implication, actually, the point Danny mentioned was implicitly used. So the main theorem is about family of spin-C structure, spin-C for manifold, but now I say that E is non-smoothable as diff bundle. So here's a little tricky part, but not so quite difficult. And so as I explained last week, so I say non-smoothable, this boundary is non-smoothable if this diagram, we have this diagram. So it means the classifying map of this topological boundary E, this is a map from torus to B Homeo. This guy doesn't lift up to B diff. Okay, so this is the meaning. And of course, once you have such a diagram, you can construct some homotopical difference between diff and Homeo just by working on normal obstruction, usual obstruction theory. So that's a story. So the point, so what I have to say is how to construct such E, but very similar to the last presentation I said. And it heavily depends on topological connected sum decomposition. So let me explain that in next slide. Okay. So maybe the spin case is a little easier to explain. So if you assume that X is a spin, then actually you have homeomorphism from X to such a piece. So here I used the assumption or that the boundary of our form manifold is integral homogeneous sphere. So if you suppose that your form manifold with boundary has integral homogeneous sphere boundary, then well just as well as closed case, you have Friedman theory actually. So you have such a topological connected sum decomposition. So here is just B plus copy of S2 times S2 and N times minus negative definite. So my notation here is minus E8 denotes the negative definite E8, negative definite E8 for some N non-negative. And here W is a contractive topological form manifold bounded by Y. So again, by Friedman's theory, you can say that at least topologically, your three manifold, your integral homogeneous sphere can be filled by a contractive guy. And in the case of non-spin, we have to consider these two cases, depending on the Rohorin invariant of the boundary. So if the Rohorin invariant of the boundary is 1, then you have a similar kind of topological connected sum decomposition, S2 times S2 and 1 minus E8, and some numbers of growing up, and contractible W, topological for manifold W. And if the boundary Rohorin vanishes, then almost similar, but we have to insert fake oppositely oriented to fake CP2. So fake CP2 is topological simply connected for manifold having the same intersection form with CP2, but having different Kabi-Gieberman invariant. So here, maybe I have to remind you. So so the Rohorin invariant of Y is same with the Kabi-Gieberman invariant of such contractive topological feeding W. So using that, for example, in the latter case, if the Rohorin of boundary vanishes, then fake CP2 has 1 Kabi-Gieberman, and this minus E8 also have 1 Kabi-Gieberman, so they cancel each other, and finally you get such a homeomorphism. Okay. And now, so in any case, so what I have to mention here is in any case, you have B plus times S2 times S2, B plus copies of S2 times S2 here, and take certain diffeomorphism F of S2 times S2, which preserves orientation, but reverse homology orientation, like last week. And more precisely, just deforming by isotopy, just to take a fixed disk for such F. and just to take copies, B plus copies of F over this B plus copies of S2 times S2, then it gives you some topological family obtained as mapping, multiple mapping torus. And since now I took F so that this guy reverses homology orientation, so it concludes that the W B plus, I just write wrongly, sorry. So this should be written H plus of B, sorry. So H plus of B, W B plus of H plus of B should non-vanish, shouldn't vanish, okay. So now we could make sure that this guy satisfies the assumption of the main theorem and take suitable spin structure S. One can check the opposite inequality holds for the closure. So again, let me first explain the spin case. In the case of spin, just to take spin structure as this fractal S, then it's very easy to check. So if you take spin structure, then of course C1 vanishes, and the minus signature over 8 is greater than delta is just assumption here. Okay, just assumption. So it's satisfied. And similarly, in the non-spin case, take spin structure over this component, and for here, take n copies of the generator of H2. And similarly, n copies of generator here, and again generator here, and the take spin structure here. Then similarly, you can check this inequality by the assumption here, by this assumption. So it's very easy calculation. Okay, so now we can apply main theorem and can conclude that E is not smoothable. So that's the proof, assuming the main theorem. Okay. Right. So this is the proof of the statement about diative diffeomorphism and homeomorphism group. Okay. So next application is about absolute diff and homeo. So these are just the same assumption with previous statement about diative automorphism group. But you can at the same time conclude that the natural map from diff to homeo, absolute diff to homeo, is also not a weak homotopy equivalence. And again, just again more precisely, you can conclude that the natural map between pi n is again not an isomorphism for some n up to d plus. But yeah, again, we don't have a good way to detect in which n precisely such a difference occurs. Okay, but this is very easy to explain. So ingredient of the proof is very simple. Of course, we will use the previous statement about the relative diff and homeo. And the second ingredient is what I explained at the very beginning of the last talk. So as I said, if you consider manifold of dimension less than or equal to 3, actually this map is a weak homotopy equivalence. But the last statement says that this diative diff homeo from diff to homeo in dimension 4 is not a weak homotopy equivalence. So just putting them together, then you can conclude something about the absolute guy. So that's the story. Okay. And okay, and so here is some specialization. So as a special case, if you take B plus to be 1, then you can get a little more exact statement. So these are, again, almost the same assumption, except for this red part, B plus of X is supposed to be 1. Then you can conclude that these map between pi 0 are not surjections, actually. So pi 0 of diative diff to homeo, pi 0 absolute diff to homeo, these are not surjections. So because this is, again, as I said, so this is proven by detecting non-smoothable family over a circle, just one-dimensional circle, then you can get this type of statement. Okay, and here is an example. So let X be an arbitrary, anything is okay, arbitrary all-entities simply connected compact smooth spinform manifold with boundary displacement homologic sphere minus sigma 2, 3, 12, and minus 1 with intersection form 0, 1, 1, 0. So maybe a typical example is just a nucleus inside the elliptic surface E of 2n. But as I said, because this, so this is the OR assumption required. So arbitrary thing is okay, not necessary to be this one. And because of the this calculation, the signature of this guy is of course 0, and this is greater than the Froshov invariant of the boundary. So this is same with, sorry, the assumption, oh, I'm sorry. So here, this guy, the spin, assuming spin and this opposite inequality is the Froshov, then you can get such a conclusion. The map between pi zeros are not surjections. Okay, and so couple of remarks. So, for example, one way to produce many examples from such building block is just like taking boundary connected sum of such an X with any contractive form manifold W. Here, same notation, but here I mean smooth contractive form manifold, smooth contractive form manifold W with integral homogeneous sphere boundary. Then the same conclusion on pi 0 holds. This is because the Froshov invariant of such contractive form manifold vanishes, and the Froshov invariant is additive and the connected sum. So just so we can apply main theorem again, just the same. And another way to produce another example is, for example, taking boundary connected sum with any number copy of minus D8 with Poincare homogeneous sphere boundary. This is also okay. So after doing such a stabilization, still the same conclusion on pi 0 holds. So this is because the minus signature over 8 is just the same with Froshov. So again, the condition that Froshov's inequality is violated can be kept by doing such a stabilization. So anyway, there are so many ways to produce example using the main theorem. Okay. So until here, I described applications. So any questions about these guys? Okay. Great. So let me then go to the proof of the main theorem. Probably this is the body of this talk. Okay, so first let me remind you again, this is just a reminder of the statement of the main theorem. So now we are assuming that the boundary, fiber-wise restriction to the boundary is a trivial boundary with honest spin C3 manifolds. And the assumption is non-vanishing of WB plus of H plus boundary. Then you can get the same inequality with Froshov's one. Okay, so let's prove this. So this is the first part. So now you have a family of spin C4 manifold with boundary. Then you can get a map between infinite dimensional spaces over B. Okay, so let me denote by large F. So this map is obtained as, roughly speaking, like families of Seiberg-Witten equations times the family of restrictions of like configurations from X to Y. So a little more precisely, these function spaces are given like this. So Wix over B is some families of spaces of forms and spinors on X. So this guy forms infinite rank beta bundles over Y. And more precisely, fiber of W0 X over B is given by this one form. Precisely, I'm taking global slice, this star. And so this is one form plus a positive spinor. And the fiber of the second W1 over B is just like self-dual form and negative spinor. And of course, needless to say, we have to do some suitable solver completion, but let me omit it from notation. And the three-dimensional part is like this. The three-dimensional part V of Y is given by, again, one form taking global slice and three-dimensional spinors. Okay. And so I have to probably note that Wix over B is a family over B, but this Vy is not family over B. The reason why is very simple, just because we have assumed that the fiber-wise restriction to the boundary is trivial free manifold bundle. Okay. So now you get a map between infinite dimensional spaces parameterized over B, and take a finite dimensional approximation of this map F. Let me denote by small f. So this can be said to be a family version of the relative bar for the invariant, but maybe I have to say that since, as I emphasized many times, so now we are supposing that the boundary part, three-dimensional manifold part is just a trivial boundary. So we don't reflect any, not like topological twisting information of the boundary part. So this is a very kind of easy version of a family version of relative Barfoot invariant. So perhaps maybe someone can consider a little more difficult version just without providing that the three-dimensional part is a trivial bundle, but this time just we suppose. So okay, and again I have to explain notation. So this, well, non-fancy W0 and W1 are just a finite dimensional approximation with these guys, and this forms a finite rank vector bundle over B, and this one decomposed into the form part and the spinor part. So this is form part coming from differential form. This is real vector bundle, and this part is the spinor part. So it forms a complex vector bundle. And if I denote by THW, this means the atom space of a vector bundle W. And the three-dimensional part I of Y is, if I forget about the suspension, this is nothing but Manrescu's stable homotopy type, Seiberg-Witten Freire stable homotopy type. So I of Y actually depends on many data. But anyway, so this is Manrescu's Seiberg-Witten Freire homotopy type, and it's defined to be certain the suspension of this space I of Y. And I of Y is the S1 equivariant Conrad index of the flow obtained as a finite dimensional approximation of the formal gradient flow of Chern-Simons function. And more precisely, this depends on a metric on Y and very small number lambda, very large number mu. So these guys correspond to choice of a finite dimensional approximation of Y. But to our proof, actually, we have to just fix one approximation and don't have to consider invariance of this guy. Okay. So okay, so now we started with this fiber bundle, four-dimensional fiber bundle, and now we get the map between finite dimensional spaces. And so this is, as I said, this can be regarded to be a relative Barfoot invariant, Fermi version of relative Barfoot invariant. And what's important here is this is an S1 equivariant map, as well as unparameterized case. So this circular S1 is coming from a part of gauge transformation. So because I have taken global slice, so still we have remaining circular gauge symmetry. And just consider the S1 invariant part of this map, okay? Then you have such a square diagram. So the S1 invariant part of this bundle is nothing but just the real part, form part, differential form part of this bundle. And similarly, this is also differential form part. And this one, so S1 invariant part of I of Y, the Conrad index is very easy stuff because the real part of the Conrad index of the, real part of the flow coming from a Chern-Simons Dirac is just Morse flow. So very easy to determine this guy. Okay. And of course, you have obvious inclusion from downstairs to upstairs, and this diagram commutes. And now, let me remind you the Frosch invariant. So roughly speaking, the definition of the Frosch invariant is using the minimum degree of non-zero elements in the image of this map. So here is a map from S1 equivariant ordinary cohomology of I of Y to the invariant part. So here the restriction map. And from now on, I'm going to work over Z over 2, just for simplicity, work over Z over 2. And consider this map, and consider the image of this map, and taking the non-zero element of this guy, then Frosch invariant is used using that degree, and after some shift. And let omega to be a degree minimizer of this image. And as notation, let me use U for the generator of the equivalent cohomology of a point, circular equivalent cohomology of a point. Okay, so U is degree 2 guy. And so key point here is take some good element here, okay? So now we have such a square diagram and take this element as the beginning of this diagram. So this is roughly the S1, this tau means Tom class. So this is the S1 equivalent Tom class of this bundle, and consider product with omega degree minimizer. And now we consider this diagram. So just using commutativity of this diagram, we can conclude this red equation equalities. This is key of the story. So to deduce this red one, actually the proof is not so quite difficult. So the key point here is in general, just in general, if you have inclusion between a G equivariant bundle, G is some certain regroup, so G equivariant bundle, if you have an inclusion, then restriction of the Tom class from two into just one direct sum component is nothing but just the Tom class cup Euler class. So it's very easy stuff. But just using this stuff and starting with this guy, we get to this red equality. So let me describe it briefly. So sorry. So this theta I didn't explain. This theta is the mapping degree of F with respect to the circular equivariant cohomology. So first send this guy to left by F star, then you get to theta as mapping degree. And if you restrict that guy to downstairs, then this guy here, because this restriction is coming from the inclusion from real part to the whole thing. So so tau of real part will tau of real part will appear, but it will cancel to the right hand side. So just ignore that. Then you get to Euler class of the complex part, and just do the similar thing. So first restrict this guy to downstairs, then you get the Euler class of the complex part, and omega will be just u half to degree something, just because we take omega to be a degree here, so we get such a thing. And this part I haven't explained, but I will explain just in maybe next slide. So just wait until that time. So anyway, I have to emphasize many times. This is key. This is crucial point of the whole story. So, for example, if you take B to be a point, and if you take Y to be sphere or formally empty set, then if you suppose P plus is equals to 0, negative definite, then this red equality reduces to more simpler one, simpler equality, and this is nothing but the divisibility of the Euler class of this guy, used in the Seiberg-Witten proof of Donaldson's diagonalization. So once you have such an divisibility formula, you can reduce Donaldson's diagonalization. And instead, if you consider K pin2 equivalent to K theory version of this red one, ignoring this part, then you can get instead the fruit as a 10/8 inequality. So anyway, this kind of inequality is very crucial to deduce typical constraint in game theory, such as Donaldson's diagonalization and fruit as 10/8. So anyway, this is very important. Okay. So now we come back. So we started with this element and consider the commutative diagram. I stated we can get this red equality. And what I haven't explained is this part. So this part is coming from the remaining part here, downstairs map. So precisely I should explain. So let me write dv of y to be the vector space whose one-point compactification is giving the S1 invariant part of I of y. And another thing I have to mention is, so this S1 invariant part is actually a fiber-wise linear injection. And moreover, if you consider co-kernel of this fiber-wise linear map, then you may get the H plus of E. So this is a source of E. Okay, since now I said that the FS1 is linear inclusion. So again, you can use this key. Since it's linear inclusion and using this key, then you can extract some information of the co-kernel part of this guy, Euler class of H plus band. Okay, so this is the blue part. So, and now we are going to finish the proof of the whole story. So, but before saying that, I should remark some points. So now the H plus boundary is realized as a subspace of this one, and this is real one because so this V is S1 invariant part of the Konno index, and this is also S1 invariant part. So these guys are real vector space and coming from form, differential form. And for differential form, now the circle acts trivially. So S1 equivariant Euler class of this H plus bundle is just non-equivariant one. And since now I'm working over 0/2, so we get to Seiberg-Witten class of this guy. So this is the source of Seiberg-Witten class. And also in general, if we have a complex vector bundle, and if circle acts on W just by a complex multiplication, then in general, you have S1 equivariant Euler class of this complex vector bundle is given by such a formula, combination of Chern classes and the generator of the equivariant cohomology of a point. So yeah, this probably is a famous formula. Actually, one can even use this formula for the definition of the Chern classes, once you're assuming some knowledge of equivariant cohomology. And okay, so now let me suppose that WB plus of this H plus bundle doesn't vanish. And as I explained above, this is equivalent to suppose that S1 equivariant Euler class of H plus doesn't vanish. So now we are supposing that, So now we are supposing that this blue part doesn't vanish. So we don't lose information so much here. And then just to substitute this formula star to this red equality, then very easy calculation, you can deduce that the rank of W0 minus rank of W1 for complex parts is less than degree of this guy, just a power of U here. And because that this omega is the degree minimizer using the definition of the Fresher invariant, and just to sit down and calculate, then you can see easily that this is just equivalent to the desired inequality. Okay, so that's the whole story. Okay. All right. So is there some question for the proof here? Okay, so this is just again reminder of the statement. Okay, so then let me finish off the talk with saying some refinement of the main theorem for the spin Fermi's case using alpha, beta, gamma. Okay, so this is a statement. So from now, I'm gonna use Manrescu's invariant alpha, beta, gamma. And so before stating that, let me remind you some. So some ups. So some it's known some relations between these invariants, alpha, beta. So I will explain from the next slide a little more. But anyway, so alpha, beta, gamma is in this order, and the Fresher invariant delta is just between alpha and gamma. But in general, no relation with beta. We don't know. And so here's a statement. So let X be a compact oriented smooth formal whose boundary is B1 equals 0. So these are almost the same assumption with rational homogeneous sphere boundary, but here is crucial. So now we are supposing that S is a spin structure on X. And similarly, this family is a spin 4-manifold family. And this is a trivial spin 3-manifold bundle. Then we have those inequalities. Okay, so this is inequality about the alpha, beta, gamma. And since now I'm supposing that S is spin, so C1 of S, of course, vanishes. So these are almost similar, just the same inequality with the main theorem, but the right-hand side will be changed to alpha, beta, gamma instead of delta. And assumptions are also a little changed. So first, this one, inequality about gamma, the assumption is just the same with the main theorem. But if you suppose that WB plus minus 1 doesn't vanish, then you can get inequality with respect to beta. And if you suppose that WB plus minus 2 doesn't vanish, then you can get inequality with respect to alpha. Okay. And sorry, I forgot to say that the latter, this right inequality is derived by Matos to Fregen, and the left one is deduced just from the definition of alpha, beta, gamma. Okay. And so, for example, if you consider this first one, because as I said, delta is greater than or equal to gamma, So this inequality is stronger inequality than the main theorem's one using delta with the same assumption. And the others are different, just different assumptions. Okay. Okay. And here's some background story. So first, Cyprian analyst defined the Froshov type precisely 1/8 integer valued invariance alpha, beta, gamma for spin rational homogeneous spheres. And he used the middle invariant beta to disprove the triangulation conjecture, probably all of you know. And for integral homogeneous spheres, these guys are just integer valued invariant. And technically, Froshov invariant delta is defined using the circle equivariant ordinary cohomology, but instead these guys alpha, beta, gamma defined using pin2 equivariant cohomology, ordinary cohomology. Here the pin2 is a larger D group than the circle, and this guy acts on Seiberg-Witten equations only on spin 3 or 4 manifolds. Okay, so using such a bigger symmetry, Cyprian defined such an invariant. And so after this works, Francesco Rin showed that the Froshov type inequalities actually holds also for alpha, beta, gamma, corresponding to assuming that B plus is equals to 2, 1, and 0. So something remarkable here is now one has Froshov type inequality for indefinite form manifolds, provided that B plus is small enough, less than or equal to 2. Okay. So this is just what I have explained. And if you apply Francesco's inequality for the case that the boundary is S3, then it recovers Donaldson theorem BC. And so in other words, so this gives the Seiberg-Witten proof of Donaldson theorem BC. And on the other hand, in different contexts, Bargulier in the same paper with the one I introduced last week. So Bargulier showed family versions of Donaldson theorem BC by Seiberg-Witten. So this is a picture. So actually, so Bargulier's statement is just the case that so the boundary is S3 in the statement I showed, and Francesco's one is the case that just the unparameterized case. The base space is just a point. And so what we did is extended Francesco Rin's inequality to families along the idea of Bargulier. And here is some little more, maybe bit technical remark. So Donaldson theorem BC itself are covered by Furuta's 10/2 inequality nowadays. But if you consider closed form manifold, actually the statement of the theorem BC can be seen as a part of 10/8. But the proof is very different. So at least, even if we consider only Seiberg-Witten equations, Donaldson theorem BC should be proved using pin2 equivariant ordinary cohomology. But as you know, Furuta's 10/8 inequality is proven by using pin2 equivariant K-theory, so it's different, of course. But closed cases, just some overlap happens. But once you consider form manifold with boundary, their resulting inequality is very different from something coming from K-theory, because the correction term appearing there is alpha, beta, gamma, which is in general different from K-theoretic invariant kappa introduced by Cyprian. And also, if you consider family version, again, it's something different from a constraint coming from K-theory. Okay, so this is what I showed, summary of the spin case. So if you consider Donaldson theorem BC by Seiberg-Witten, the with boundary version was given by Francesco Rin, and the family version is given by Bargulier. And what we did for spin is here in this picture. So let me show you some example. So an example detected by gamma, but not by the Froshov invariant delta. So this is a building block. So let X be an oriented, compact, smooth spin for manifold with boundary, 2 copies of sigma 2 3 11 with intersection form of this guy. One example of such X can be get from just inside the K3 surface, considering some nucleus. And using Matta-Stuffagen's connected sum formula, you may calculate gamma invariant for the boundary, and it turns out that this is less than minus sigma over 8. So this means the desired inequality is violated. So then you can obtain similarly like the mark between pi zeros are not surjections. Okay. And so something interesting here is this doesn't follow from the Froschhoff invariant, because the Froschhoff invariant of the boundary is just the same with minus sigma over 8. So the Froschhoff invariant inequality doesn't violate it, but the inequality involving gamma is violated here. Okay. And so as I said, this is building block example. Because, for example, if you take such an x from inside K3, this just follows. This statement on pi 0 follows from Donaldson result on K3. But as I said in the last example, actually this is very flexible. For example, you can take the boundary connective sum with minus E8 with Poincare homomorphic sphere boundary. Maybe there are many ways to generalize or extend using this building block anyway. But even doing such a stabilization, still the conclusion holds, because again, the gamma's inequality is just violated. And again, Froschhoff invariant is just the same with minus signature over 8. So again, this doesn't follow from the constraint coming from delta Froschhoff invariant. Okay. And similarly, in such a way, there are so many examples like one can also get the example detected by beta, but not by gamma. Just similarly, taking something looks like inside K3 and just a very similar story. And again, you can stabilize by minus E8 boundary connected sum. Okay, but in this case, so if you use invariant beta, you can get some conclusion about pi 0. But once you consider gamma, actually, gamma also can be used to get something. But in that case, you can only state that you can only show that at least one of the map between pi 0 and the map between pi 1s is not isomorphism. So of course, this is weaker statement than only the statement about pi 0. So if you use invariant beta, you can get little more beta thing than using the result using gamma. Okay, and okay, here is a very brief sketch of the proof of the refinement. It's quite similar to the proof of the main theorem. So let me just only list up the key points. So take 3, we have to take, so I took some degree minimizer omega, but in this case, we have to take 3 different elements in pin2 equivalent cohomology of the Konno index corresponding to the alphabet gamma. So these are degree minimizers of the 3 V towers. So V is the one with the name of the pin2 equivalent to cohomology point. And another point I have to say is pin2 equivalent Euler class of this boundary H plus is it's different from the last time, because now pin2 acts on differential form by ±1 multiplication. And using that action, you can say that the pin2 equivalent ordinary cohomology of this guy is given by such a formula inside pin2 equivalent cohomology of the base space, which is given by B like non-equivalent cohomology polynomial with variable Q and P, and Q cube is 0 and V is non-torsion. So anyway, you can get such a formula, and just combine these two stuffs with proof of main theorem, you can get such a refinement. Okay, now it's precisely the time. So this is just a reminder of the statement again. Okay, so this is the end of my talk. So thank you for listening over 2 weeks, and I hope see you face to face in the near future. Yeah, thank you so much.
Other questions?
I have a question. Do you think that there might be analogous inequalities involving the kappa and kappa O invariance in the equivariant K theory? Would be some kind of families 10/8 type theorem?
Yeah, it's a good question. Yeah, I think probably one can get as an abstract statement. So that's our guess. However, the reason why we didn't work on that part, like k-theoretic version of those statements, is just a practical reason. We couldn't think of a good example to which we can apply expected constraint coming from k-theory. This is because, so what's good point for ordinary cohomology is we can work over z over 2, but as you know, in k-theoretic case, we don't have such a simplification. And well, so let me show you an example. Currently, the example we had is very, very simple one, such a one. So we considered such an example, and in our example, something important is taking different morphism reversing homology orientation. So it means that the resulting H plus bundle is not oriented even in ordinary cohomology sense. So of course, no hope to get the k-theoretic orientation for such a guy. So just such simply k-theoretic orientation problem, we don't have any good idea to construct a good example detected by k-theory.
Okay, thanks.
Yeah, thank you.
I don't want to cut off questions, but I will remind people that we'll be back at the same time on February 2nd. We'll also be back on February 9th. Juanita will be speaking then. Are there further questions for Hokuto? It's certainly worth saying thank you.
Yeah. I think those are two great talks. So thank you very much. I would clap again. So yeah, thank you very much.
Yeah, thanks so much.
Anyway, so we'll see you all, yeah, on Tuesday, the February 2nd. So thanks again, Hokuto. That was a really nice talk.